show that the space Rn minus m points is simply connected when n is greater or equal than 3. And this statement is not true if n is less or equal than 2. I recall that simply connected means path connected and pi1 of the space should be 0. So for example, if we look to n equal 1, R minus m points will be a collection of open intervals, which is not connected, clearly not path connected. So this means that in the case n equal 1, the space is not simply connected. In the case n equal 2, suppose we take out 2 points from R2. So we will have the space and the 2 points that are missing. We can do the following. Divide the space in 2 and project everything on 2 circles that go around these points. So we divide into the space, and every point in this part we project it on the circle, and every point on this part we project it on this circle again, and we do this also for this. So in the end, this projection will tell us that R2 minus 2 points is S1 wedge S1, a wedge of 2 circles. We can do the same for R2 minus 3 points. We can divide the space in 3 parts, and we can project on circles that are around these points. So we project all the points on the circles, the interior points on the circle, the exterior point on the circle, given by the division that we get. So in the end, we will get that R2 minus 3 points, it's homotopy equivalent with 3 circles. So this means that if we take a wedge of 3 circles, so if we take m points out of R2, we actually have to compute pi1 of S1 and S1 n times, and this in conclusion will give us Z star Z star Z. So the space R2 minus n points is path connected, but the pi1 of this space is not 0. So this means that in the case n equal 2, the statement is not true according to the theorem. So now let's move in the case n equal 3. So we will try to take out 2 points out of R3, and we will try to do the same method on this space. So suppose we miss these 2 points in R3, we divide by a plane the space in 2. So now what do we have here? So we will have a sphere on which we project all the points. So all the interior points will project on the sphere, and all the exterior points in this division of the plane will project on this sphere. So in the end, the homotopy of R3 minus 2 points will be S2 wedge S2. So if we take n points out of R3, doing the same method means that we will have a homotopy with S2 and S2 and S2 m times. So the space will be always path connected, but the problem is that if you take pi1 of R3 minus x1 xm, this is 0, because pi1 of S2 is 0, and we will have a free group of pi1 of S2. generated by pi1 of S2, which is 0. So this means that pi1 of R3 minus m points is 0. So similarly, if you move to n dimensions, we will do the same method. We will divide by a hyperplane the space Rn plus 1 around these points, and we project on the corresponding sphere. So in conclusion, we will have something like Sn, wage Sn, and this is k times. The space is path connected, and if you take pi1 of this space, Rn plus 1 minus x1 xk, this will be the free group generated by pi1 of Sn. So, and pi1 of Sn, according to our lectures, is 0 if n is greater or equal than 2. So this means that this is 0 for any n greater or equal than 2. So in conclusion, the space Rn minus any m points is simply connected if n is greater or equal than 3.